Webcast? How do we know if they start the webcast?
I saw it.
All right, so it looks like we're starting. Welcome to our Friday Transportation Seminar. And my name is Robert Bertini, and I'm a faculty member. And along with Chris Monsier and Jennifer Dill and Miguel Filiozzi, we organize this weekly seminar. And we've been doing this for a long time. We're coming up on our 200th seminar in a few weeks. And so, as you know, all of our seminars are available on our website as webcasts, as will this one. And today we're very happy to have Zong Tian from the University of Nevada, Reno. He's here to talk to us about signal control strategies for operating closely spaced intersections. It's all yours.
Okay.
Thanks.
Thank you, Rob. Yeah, thank you for inviting me to come here to present something in this really, I call it world-class seminar series. Okay, because I haven't really seen anything like this in any school. Not only you got all the quality speakers, but also it's sustained for such a long time. It's a lot of work. Okay, so you guys are lucky here. Anyway, just a little bit about myself. I started my career here in the United States, actually with studying stop-controlled intersections, stop signs. So I came here in 1992. I did my master's degree at the University of Idaho. I don't know how many of you know where University of Idaho is. Yeah, before I came, I looked at the map. I saw that's in the kind of a corner of the map, and they gave me this project. It's a big project, but still it's dealing with stop-controlled intersections. So I thought, maybe there's no freeways there. There's no signals there. That's why they gave me this stop sign project to work on. Okay, of course that's not the case. Okay, so I spent about 2.5 years there, got my master's degree. Then I started my professional life at Kittleson Associates. Probably most of you know, just in downtown here at the office. I spent about 5 years here, and that's when I started to see the light, the traffic lights. Okay, and I have been always fascinated about traffic signals. I was always curious about how those computer optimized signal solutions being implemented into the field, into the signal controllers, how they are really working. So since then, I've been really working in this field for a while, and I went on to get my PhD degree at Texas A&M University. Now I'm in Reno, Nevada, University of Nevada, Reno. And I've been making a lot of presentations at seminars, conferences. I kind of committed myself. I usually tell the audience, yeah, next time I'm going to present something, it has to be related to signals. So here I am again. So I'm going to talk about the signals. And today, actually, I'm going to talk about how to operate and control closely spaced signals. You'll recognize this picture. I put this picture because I want to remind me to ask Rob. I never asked him, is this actually real?
Yeah, it's in London.
Okay. Yeah, I've seen that signal tree many places, but I never has been wondering, is that real? So I saw this picture. So.
Canary Wharf area.
Okay. So that's real. Okay. Anyway. Here is kind of a quick overview about what I'm going to talk about today. So I will talk about the issues and challenges related to closely spaced signals. Then I'm going to present to you some case applications, and finally give you a kind of a final thought about where should we go with on this topic. Well, the issue, okay, the closely signals is probably you've seen it everywhere, okay. Really, the things we are dealing with mostly are the queues and the stops. Okay, if the signals are really closely spaced, so the queue can cause queue spillback and blocking the intersections, can create a lot of safety concerns. Okay, so that's really the major issue. And also, queue spillback can significantly reduce the efficiency of the signal. If the intersection is blocked, you see the green, but you cannot go. Okay, and another thing is the stop. Okay, if you drive through a closely spaced intersection, for a typical driver, you are expecting to go through the next one without stopping. But if you stop, then you got frustrated. And this can be easily noticeable. If the signals are far spaced and you stop at next signal, probably you'll say, well, that's reasonable. I'm expecting that. But if they are really closely spaced, okay, you don't expect to stop after you start from the first signal. So we have these kind of issues we often deal with about the closely spaced signals. Now the challenge to operate and control these signals. One thing is it's difficult to coordinate, okay, because really we need to find ways to manage how to manage the queues, how to minimize the stops, okay. And another issue is, we all know typically one controller will provide a much better coordination of two closely spaced signals. But there are some issues related to using one controller. Okay, the one issue, we got a lot of wiring going on. All the signal poles, signal lines, the detectors. There are a lot of wires going into this cabinet where the signal controller is located. Okay, can the cabinet handle all those wires with two signals if we use one controller? And also, where do we find a place to place the cabinet? You need to find a place so that you can at least see both signals at the same time. Okay, so these are the challenges we are facing. And what I'm going to talk about today is actually some special cases of closely spaced signals, where we can have certain kind of strategies to control and operate them. Okay, the first one I'm going to talk about is the interchange. Okay, interchange. And the first type, a common type interchange, is a diamond interchange, where you see the two signals. Okay. The two signals, usually, especially in the urban area, they are pretty closely spaced. And then the other type is like this. We call it the partial cloverleaf. Okay. Still, you have two signals on both sides, even though the configuration is a little bit different from diamond interchange. So a lot of studies have been done related to diamond interchanges, but not so for a partial cloverleaf interchange. The second type, the T intersections. Probably you have seen this type of configuration a lot of places, right? You have two signals and two T-type intersections. They are closely spaced. Okay. So these are the things that I'm going to focus on for today. I know the audience pretty much, the majority are students. So probably you have learned something, just the basics about signal timing. Okay. Anyways, I'm not going to get into the details, just quickly go over these things. To do coordination, to operate the signals together, the most important parameters, cycle length, okay, the phase, and the offset. So you know, you have some idea about these terms, or do you? Yeah. Okay, good.
Actually, there's a mix of students in here. They're not all civil engineers, so maybe very quickly.
Okay. Okay, then it will take a long time. That's good. Cycle is mainly, if you try to coordinate the signal, they must have a common cycle. The cycle is from one movement go through all the other movements, how long it takes, the cycle length. The phase is for particular movement, how much green time you are going to give to that movement. Then the offset is between this signal turns green, how many seconds later the other signal will turn green. So just in general. Okay. And then the type of left turn control. It's mainly when we deal with the coordination. Okay. Really, we are really dealing with left turns. How are we going to do with the left turns? Okay. Are you familiar with the type of left turn controls? Permitted, protected, permitted. Like this. Permitted, right? Permitted. What does that mean? You can still make the left turn, but you have to watch the opposing traffic. So that's what it means. But do you know how to drive? Most of you drive, right? Okay. But when I first learned how to drive, I understand that I can make a left turn, but I didn't know whether I'm supposed to get into the middle of the intersection or stay at the stop bar. So one day I just decided to drive, to take a drive. I couldn't remember whether I really got my driver license at that time or just a permit. I couldn't remember. But I remembered one day nobody was willing to come with me, so I decided to go to drive myself. And I came to this intersection with the permitted left turn control. And I didn't want to cause trouble. I didn't want to get a ticket, so I was very, very careful. I was waiting there for a large gap, but I didn't pull my car into the middle of the intersection. I was staying at the stop bar. So one cycle passed, the second cycle passed. I couldn't get a gap large enough that I feel comfortable to take the gap. Then suddenly I heard the lady pounding my car. Hey, young man, when the light turns green, you need to pull the car into the middle. So that's my first driving experience. Okay. Yeah, probably you'll understand, but a lot of people actually may not know the details about this kind of control. This is the protected. When you see the left turn arrow, you can make the left turn. You don't have to worry about the opposing traffic. The opposing traffic is supposed to stop. But that's not the case in China. I don't know whether, Robert, you remember when we were in Tian, we saw this left turn arrow. Actually, both directions are moving. So the different countries, they may have different meaning. How about the protect the permitted left turn? When sometimes you see the left turn arrow, then the green ball. Okay, so you think, this is easy to understand. But FHW actually spent several years, close to $1 million just to standardize the display of a protect the permitted left turn control. So type of left turn control, the three common types. And then the other one is the facing sequence. Okay, should we turn the left turn first, then the through, or should we turn the through first and the left turn? So these different kind of facing sequences are all important for coordinate signals. And the next I'm going to introduce the phase, the signal phase. But again, I think you all have some kind of idea, but I still want to go over this material since I'm going to talk about the phases. So signal phase and traffic movements, they are kind of related, but they are not the same thing. Okay, this is a typical full intersection where we have 12 traffic movements. Okay, but exactly how many signal phases do we need to control a full intersection? Anybody knows? Huh?
It depends.
Depends. Yeah, the maximum number of phases you will need. Maximum.
Oh, maximum?
Uh-huh.
2. Or no, that's sorry.
Okay. Yeah, we have 12 movements. If each movement is protected, we don't want to cause a conflict. Okay. The number of phases is actually 8 phases. 8 phases, that's all we need to control a full intersection. Why do we need 8 phases? Because the right turns, for example, the right turns, do we need a separate phase for the right turns? No, because the right turns, they can just go whenever the through goes. So the right turns can just follow the through. Okay, you don't need a separate phase for the right turns. Then we have 8 movements left. And if we want each one of them to be protected, no conflict, then we got 8 phases. And this is the kind of a convention, NEMA convention. We call the NEMA convention, where how to number the phases. As you can see, the even numbers are for through phases, and the odd numbers are for left turn phases. And in some phases, they can move together. Some phases, they are conflicting each other. Like in this case, this left turn can go with this through. There's no conflict. This left turn can go with that left turn. There's no conflict. So how can we effectively to eliminate the potential conflicts? And this is what the phase ring diagram. So some of you have learned this. Yeah, if we run the signal like this, okay, phase 2 always phase 1, phase 5, phase 6 always phase 6, and then this barrier, that means you stop this direction, you go to the other direction. There will be no conflict. So that's the phase ring diagram, the theories behind this. Okay, the other one I want to mention is called overlap. I mentioned earlier, the right turns, we don't need a separate phase. But how about if we want to provide protection for the right turns so that the right turns will not conflict with the others? And in that case, we use called the overlap phase. Overlap phase means it can go concurrently with at least two other phases. In this case, so this right turn can go whenever the through goes. What's the other phase it can go without a conflict? Can go with the other phase.
Right and stop now? With the one and five.
With this one?
No. With one and five.
One in the bottom.
If one and five are on, then the right turn can be protected, or will not have a conflict.
Okay, you are talking about the 5?
Yeah.
Yeah, that's the one. That's the one. When this 5 has the green, so this right turn can has the green, no conflict. But not this left turn. Okay, not this left turn. If this left turn goes, that means this 6 can also go, so it's going to cause a conflict. Okay, so this is called overlap. The reason I want to mention this is when I talk about the diamond interchange, so we have an overlap. We use overlaps to control some of the movements. So this is a diamond interchange. Doesn't look really like a diamond, but any intersection, any two signalized intersection, if they have this kind of characteristic, then it can be controlled using the diamond strategy. So what we have here is we have a two-way arterial street. Then the cross street, two cross streets here are all one-way streets. As long as you have this kind of configuration, you can use the diamond phasing. Okay, but not many people really know this. Even the engineers, they work in the field for many years. They are not aware of this. Okay, let's look at these two movements. Okay, these two movements. Do we need a separate phase for these two movements? Okay, for the other ones, we know we all need the separate phases. So for this signal, we need 3 phases. For that signal, we need 3 phases. But for these two internal throughs, we can actually use overlap. Again, overlap is the phase that can run concurrently with at least 2 other phases. Okay, so in this case, that overlap is phase 1 and 2. So when 1 and 2 goes, that movement can go, no conflict. The same thing on the other side. Now, you can see how many phases do we really need for controlling both signals. 6, right? We have only 6 phases. I mentioned to control full intersection, we need 8 phases. And that's the minimum, usually the minimum specifications for any signal controllers. You must have a minimum of 8 phases. Now, with 6 phases, using one controller, we can control both. Okay. And then there's 2 other phases. We call it the dummy phases. And that's when used on a special diamond phasing that I'm going to talk to you next. So they are really not real phases, but it's a dummy phase. And some people call them overlap. So the overlap is a confusing term, really. This diamond phasing I'm going to show you is called the TTI 4-phase. With this phasing, so you can guarantee that no vehicle will stop in the middle. Okay, no vehicle will stop in the middle. That's really effective when the signals are closely spaced. So you don't want the people stop in the middle causing queue blockage. Okay, this is how it works. See, I mentioned that dummy phase here. So this dummy phase is really when this is on, you can turn this on. So you can serve both movements. And by the time the car gets here, then you stop that dummy phase. So that's kind of fixed. Then that car will go through without stopping. Now you turn to the one side of the frontage road, so that is already green, so that movement will not stop. And then the last portion is the dummy phase on this side. You turn the arterial on. Okay, the car gets here, that dummy phase turns right, so the car will not stop. Then you move to the other approach. So you go like this, clockwise. So no car will stop. Okay. So it's really effective for controlling closely spaced signals. And next I'm going to present to you is the study we did at these closely spaced signals. Okay, I know some of you may have already seen this part of the presentation, but I never had enough time to tell the whole story. So I'm going to tell you a little bit more about the things related to this project, what we did. The UNR is here, UNR campus. Reno downtown is here. How many of you have been to Reno? Only 3. Okay. Yeah, if you come to UNR or go to Reno downtown, you have to go through these signals. Okay. The spacing is approximately 300 feet apart between all the signals. And the street, this is really the freeway off-ramp. They named the 8th Street, and this is the Maple Street, which is on the other side of the on-off ramp. This is Virginia Street. It's the main arterial going through downtown. Then this is Center Street. This is Sierra Street. Okay, 6 closely spaced signals. Yeah, this is what the existing, before we did the timing. That's how they control it. Okay, you probably you don't want to read those phase numbers, but mainly they used 6 controllers, with 1 controller controlling each individual intersection, and those are the phases. Okay, if you look really carefully, for example, Virginia Street, this is a 2-way arterial. Okay, we have left turns, internal left turn here, then this is 1-way, this is 1-way. That's a diamond, right? That's a diamond interchange, even though they look like 2 signals, but that's really a diamond interchange. Okay, so I noticed this immediately after I moved to Reno. I said, well, this intersection, these 2 intersections really need to be improved. Okay, so I talked to the city, and that's how we got this project. But if you look at the other 2 signals on Center Street and Sierra Street, they are not a standard diamond interchange. For example, here, this is a 1-way street going north. There's nobody can go south. So there's no through movement here. Because you cannot go through, then think about the left turns. Where did they come from? It's mainly from here. It cannot be from the freeway unless you get lost, right? Yeah. So there's no left turn here. So this is not a diamond. On this side from here is a 1-way. There's nobody going north, so there's no left turn here. Again, this is not a diamond, standard diamond. But somehow we apply the diamond phasing to these 2 locations and to control all these signals. And this is what we did. So we proposed to use 3 controllers to control those paired signals. And for the Virginia, we know this is a standard diamond, so we use the diamond TTI for phase. And for the Center and the Sierra, we use a modified diamond phasing. Okay, this is what we proposed. Again, you don't have to read all those phase numbers in detail, but generally we propose using 1 controller to control this, 1 controller to control these 2, 1 controller to control these 2. And you can see the dummy phases, phase 16, phase 12, we added there. Okay, just try to simulate the diamond kind of phasing. This is looking at Virginia Street, 2 signals, and I told you this is a standard diamond phasing. But this was what's happening before. Okay, you can see the queuing stops in the middle. This left turn is a kind of lagging left turn. They are waiting for the gap. They got the green. They are waiting for the gap, but they can never find a gap. So they queued up there, blocking the intersection, and those cars got released to the middle, and they also queued up in the middle. That's before. Okay. After. So this is after we put the diamond phasing. This is what's happening in the after case. As you may notice, when this frontage road, this 1-way street is moving, actually we didn't release these cars. If we release them, they are going to stop anyway. So keep them. And by the last portion, with the dummy phase I was talking about, phase 16. Okay, now see, actually it's running phase 16, so you start this. By the time they get there, you stop that movement, and this car will get the green, so they will go. Okay, they went a little bit too fast, so they had to stop. Okay, yeah, you should follow the speed limit or go a little bit slower in order to avoid the stop. And then actually we can show a kind of side-by-side comparison. Yeah. The reason we could do this is because the before and after we used the same cycle length. And I was able to synchronize the starting point of the cycle. So you can see actually they are really starting at the same time. I was able to synchronize two videos. But look at the difference here. First, this left turn is lagging. They are waiting for the gap. They couldn't get a gap. And for the northbound, the before case, they released too early, so they stop in the middle. Versus here, you hold them and release them before that phase is going to terminate. Okay, so these are the differences. Now for the other two streets, signals on the other side. Okay, this is looking at the center street on the right side. Okay, I talked about here is a one-way street. There's only left turn here. There's no left turn here. Okay, so this was the this were the traffic movements, but this is what we proposed. I marked the red portion is when the vehicle do stop. All the green portions the vehicle can go. So which vehicles will stop are those ones. So phase 4 here, the people making left and going north, because when they're making left, that frontage movement is moving, so they will stop. Seems is a big red, but if you look at the number of cars, it's only 41 cars in an hour. So it's really not that bad. Then all the other movements pretty much can be progressed. For example, if you're going north, you can go through. You stop only if you arrive at the last portion of the green. If people coming from the south, yeah, they can go through. Okay. And this is I shouldn't put the sound. Going north. Okay, going north. You can watch there. By the time they get there, that will turn green. That's kind of a dummy phase I was talking about. Okay, they go through. You stop only if you arrive at the later portion of the phase. You stop. Like this car, he may stop. And then this will turn red, yellow, red. Okay, now we know people coming southbound, we already have the green there. So you can see those cars, when they get there, it's the green. Okay, let's get rid of the noise. That's for Center Street. Sierra, again, we use the diamond facing strategy to do the Sierra. The only movement that you can see that they are going to stop is actually this movement. This movement from this one-way road, which are mainly the people coming from the east from freeway, they are going to downtown, making left turn going downtown. If you are in the later portion of the cycle, you are going to stop. Otherwise, all the other movements will go through. Like this one is the people coming from west going north. They are going through. And yeah, they all go through. It's guaranteed. And if you are coming from the freeway here, you can go through unless you arrive at the later portion of the cycle. So that's on Sierra Street. Okay. And then this video, what I'm going to show you is actually, it's not what we are proposing, not what we proposed. Okay, I tell you why it's not what we proposed. Okay, because see now we start this phase. This is the eastbound. Okay, what we propose is actually to hold those cars. Don't release them. If you release them, they are going to stop anyway. Okay. But with the current phase, you cannot stop them because there are only two through movements here. If you turn the northbound green, the southbound will be automatically green. Okay. What you can do though is, this is what we proposed. You put instead of using phase 2, use the overlap to control that movement. Phase 4. So phase 4 cannot go with phase 6 together. So you hold those cars. Okay. Somehow I wasn't able to convince the city we can do this, so they were all worried about rewiring the cabinet, those kind of things. Then I thought about it. Okay, maybe I shouldn't really push them. Just leave something, leave a problem area so that at least when I teach a class, I can show the students the bad side of the signal timing. So I didn't push that hard. But recently we got complaints. Some people say, I always stop in the next signal. Yeah, and maybe we have to do something. Yeah. So that's Sierra. I just talked about using 3 individual controllers control those paired signals. Then the next one is how can we come up with the timing so that we can progress the majority of the heavy major movements. So this is what we did. Look at the major movements. This is one of them. People coming from east on I-80 freeway going downtown using Virginia. That's about 284 cars per hour. That's a pretty major movement. The other movement, people using Sierra going to downtown. That's about 400 vehicles per hour, major one. The other one is people coming from Virginia, which is usually people work for the university and then go back home using the freeway. That's about 300. So we try to progress those major movements. Of course, we cannot take care of everybody. So some movements have to suffer. So that's just the nature of signal coordination. We try to take care of the major movements. Okay, so you can see here, I'm looking at the 8th Street. Okay, I don't know why it is. Oh, what happened? Okay, I'm looking at the 8th Street, how the traffic will go to the next signal and then make a left turn on Sierra and then go to downtown. So they should be progressed without stop. Yeah, I couldn't see the other signal at the first signal because I was standing on the parking garage. So I couldn't really see the other to track the entire movement. Yeah, I wish I had a helicopter, flying over. I can see everybody. But that's the movement. It's progressed, guaranteed, no stop. Then look at the Virginia Street. Okay, this is Virginia going south and turn left, going to freeway. Again, I can only track. This one I was able actually to track the entire movement. They come to this signal. Yeah, they do stop shortly. This is kind of for efficiency. Yeah, I think I don't want to talk too much. Once they make the left turn here, you go to the next signal, should be green, should be already green. So they can be progressed without stopping. So these are the major movements I talked about earlier. Take care of the major movements. Okay, so they go through, no stop. Okay, the next issue I want to touch is with this kind of system. We look at the 6 signals. They form the kind of a grid system, very similar to the signal systems you see in downtown Portland. It's a grid. In this case, is it still a good idea to run actuated coordinated or just simply run fixed? Okay, I'm not sure whether you're clear about the difference between fixed time versus actuated. Actuated is when you have detectors. When there's no car, you don't get the green. Or when the car is gone, the green will terminate. We call it gap out. Okay, with this kind of grid system, okay, it's really not a good idea to run actuated. And this is what's going to happen. Okay, I start with the first signal, green. Okay, that's not my car. Okay, you couldn't see my car because I'm taking the video in my car. Now you see the next signal. Okay, if you pay attention, that's green. That's green. Okay. However, I didn't drive fast enough to get there before the phase gapped out. And then right before I reached the signal, the phase gapped out. I had to stop. Okay. So this is the problem of running actuated. But if we run a fixed time or put a max recall for that phase, then you don't have this problem. once you go through the first signal, you can go through the next one, like here. That green will keep there to let me get there and getting through. See, even I didn't. Did I stop? That's different video then. No gap out. Yeah, I just repeated. So this is actually no gap out. Okay. It's okay. You watch it twice, so you remember the experience of stopping twice. So this is the one I was talking about. Yeah, put a max recall around a fixed time so that it won't gap out. So that green will remain. Okay, you can get through without stopping. All right. The next one, again, is related to whether it should run actuated or fixed time. Okay, this is a kind of illustration of a case. We where? I went too fast. This is the time we allocated to the cross street. Okay, if we run actuated when there's no car on the cross street, so that phase will terminate. Will result a car going like this. You get to the intersection, you stop shortly, and that cross street phase terminates, and then you move on again. You get to the next one, you stop, and then go through. Okay, so the delay, that's the amount of delay, right? The delay is between the ideal travel time and the actual travel time. That's the delay. How many stops? 2 stops. How about if we do this? Even there's no car, I will keep that phase on. So hold this vehicle. And once I release it, okay, make 1 stop, then you hold it. Then you release it. Then you can go through the next one without having to stop. What's the delay? The same, right? The same amount of delay, but 1 fewer stops. Okay, and this is what happened. What happened? This is the early release case. See, there's a cross street, there's no car, so that phase gap out, and the green turns on this main street. The car will go, but you can see the downstream, the cross street is moving, so they have nowhere to go. They stop in the middle. And when the link is very short, it's very, very easily to cause this queue blockage, spillback. Okay, so that's an early release. But how about if we hold it? Okay, this is no early release. See, there's no car here, but don't terminate that phase. Hold the cross street. And when you release it, make sure they can go through the next one without stopping. So you do delay a little bit longer here, but once it's released, you go, and the next one will turn green. So you can go, you can progress. Okay. Okay, so this is a kind of a case about applying diamond phasing to an actual case. Okay, I also mentioned the other type is T intersections and partial correlative interchanges. Okay, like in this case, how many phases do we really need? Can we use one controller to control both signals? If we really look at this, yeah, these are the phases we really need, 6 phases. And we can use overlap to control those 2 movements. So one controller is enough to control both. But how many engineers really know that? Okay, not actually. You will see a lot of people, they don't know that. How about this? You have also seen this kind of T intersections. Okay, again, one controller, you can do that. How about this? Okay, so similar. But this one, I couldn't draw that partial clover leaf. It's mainly one side you have the internal left turn, the other side they make instead of left turn, they make a free loop, right turn. Yeah. How can we use one controller to control this kind of interchanges? Again, not many people realize they can do this. Yeah, this is kind of my suggestions. Okay, of course, I cannot go through the details. Okay, just to give you some kind of a final thought based on the things I presented. Yeah, the first one is I already talked about it. Actually, diamond facing we have studied for a long time, but still a lot of traffic engineers, they are not aware of this kind of facing. And they also don't know how to actually apply to similar cases. Okay. The other thing is if the signals are closely spaced, usually the stops and the queuing are more critical than delay or travel time. Okay. You know, travel time, delay, they are more important. When you evaluate the performance of a signal system, you usually do the travel time run. But when the signals are closed, stops and queuing are more critical. And also in terms of using one controller versus two controller to control closely spaced intersections. And this is the area actually needs more research. Okay, I have been thinking about this topic, but I haven't been able to get some funding to do that. So that's a area needs research. Yeah, our project did get a lot of exposure to the local media. Do you want me to show this, or have you seen this video? About 2 minutes? Yeah. Okay. So, some of you may have seen this if you visit my website. So this is the kind of a local TV report about the project we did.
Ask most people around here about traffic, and they will say we have a whole lot of construction and a lot of red lights. The Regional Transportation Commission has been working on retiming some signals, and now some students from the university are getting involved. Tom Hankenius looks at one intersection where help is coming.
Green means go, but more often than not, as you approach, they turn yellow, then red. Dr. Zong is a professor of traffic engineering at UNR. He's been here 2 years and noticed at some intersections the timing is off.
So I thought, yeah, we need to do something here.
So Dr. Tian and his students, working on a grant from NDOT, decided to take on the signals that make up the intersection of I-80 and Virginia Street with one goal in mind.
To minimize the delay of the people and the interchange.
The students measured the traffic, then plugged that into a computer model. But that's a little hard to understand, so take a look at some video they shot. On the left, before the retiming, on the right, after. And the before screen, notice the line of cars waiting to turn left. Now, look at what happened when the signals were retimed. After a short pause, the signal changes and the traffic keeps moving.
We don't want people to stop in the middle.
You shouldn't stop at all.
Yeah. Only if you enter the intersection at the end of the green, you may experience some stops.
They say the same timing could work at other I-80 intersections with Wells, Rock Boulevard, Sparks Boulevard. Is there more work to be done?
Yeah, sure. This is why we're here, yeah.
Now, because of some road work being done on Virginia Street downtown, the signals have actually been turned off. It'll be another 2 weeks before they get turned back on. But once they do, we're told, look for some quicker movements through downtown. Covering the story, Tom Hankenius, Channel 2 News.
Okay, so that's a kind of a TV. Finally, a kind of a commercial. Okay, yeah, this is our group, the transportation group. We don't have as a large group as you guys here, but we are getting along okay. Yeah, this is I call it the master signal controller, and then coordinated with all the others. And there's one guy. Yeah, he dropped out of coordination. He just graduated last semester, so he went to work for the profession. That's all. Any questions? I'd be happy to answer any questions.
And remember to use your microphones if you have one nearby. So we have a portable one.
Thank you. Well, I just don't know about that delay. I felt as if it's the same. It didn't change in the case of the diamond interchange. when we let the people not stop in the middle and just proceed going, how much did we benefit from that? I mean, did we reduce travel time or reduce delay? I felt that they stopped either way. It's the same. I mean,
yeah. Okay. If the volume is low, you have enough capacity to handle the traffic demand. So mainly the delay will be very similar, but you have fewer stops. Sometimes when we do this kind of timing, we do lose some of the efficiency. So if the volume is getting high, when the volume is reaching to that capacity level, the delay could be longer. So there's only conditions that you can use this kind of a strategy. You shouldn't get into the situation where the demand is over capacity, then your delay will actually increase. So the purpose is mainly to reduce the stops, but delay pretty much the same. Is that what you asked?
yeah. I mean,
No follow-up?
yeah. I mean, we didn't really reduce the.
We didn't reduce delay. Yeah, that's
Yeah,
true. That's true.
so-
But we reduced the stops.
Okay, so maybe people feel more comfortable
Yeah,
to
what-
not having to stop a lot. And
Yeah. Do you drive?
No,
Okay, you don't drive.
I use public transportation.
How many people care about 5 seconds more delay versus to treat one less stop, right? Stop is actually people care more about stops. If you really look at, if you drive, I believe you have this kind of experience. Yeah, delay really not much change.
That was my question. Do you know of studies that, like the psychological effect of having multiple stops? I mean, you mentioned that just in your observations and talks. Is there data for that too?
Interesting. There's a study related to that. It's an NCHRP study. They try to evaluate the level of service on urban streets. So that they actually took the video. They sit in a car. They drive through the system. They take a video, and then they don't tell the driver. They survey the people. They don't tell them. Okay, but they ask the people to watch the video. Tell me, what kind of a level of service do you feel? So in the video, when you stop, they know they stopped, right? And also they have a travel time. And then eventually they found out that stop really jumped out. When they did that regression analysis, they found out speed is, people don't care about the speed. Travel time, they even didn't notice the difference of travel time. But if they made stops, they really noticed that. So there's an NCHRP study, and there's a TRP paper. I can give you that paper if you want to read that one. So that's where, we do have some data to quantify that. Mm-hmm. Okay.
I'm just curious about the controller. How does controller work? When if there's a coordinated signal, so does that mean need two controller to controller coordinated together, or just a signal coordinated together? Behind each signal there's a controller, or maybe behind multiple signals there's one controller. When we say coordination, it's really coordinating those controllers, because the controller is controlling the signals. So we are really talking about controllers. Okay, so if the two intersection with two signal, they coordinate each other. Actually, there's two controller coordinated.
Yeah.
Questions from someone on the web, and I think one of them sort of follows up on this question. For the diamond interchange, when we use the group controller, one controller for two signals, do you take into account the travel time within the two ramp terminals? Do you take that into consideration?
The travel time in terms of do the timing or the performance?
I think into the timing.
Timing. Yeah, the timing, you see that dummy phase I was talking about, that dummy phase, the length of that phase actually exactly equal to the travel time between those two signals. So that, you travel, you use that phase to serve both movements, but when you terminate that one, the car exactly gets to the other one, so they don't stop.
Okay. And then the other one, for fixed timing signals, do you change the timing plan during the day based on traffic patterns?
Yes.
We do have 3 timing plans developed: the AM peak, midday peak, and the PM peak. Yeah, but during those periods, it didn't run actuated, so it's all fixed regardless of the traffic. That's because of that grid nature. And you've noticed the downtown Portland is a grid system. It's a fixed time, mainly fixed time operation. You move out downtown, it's all actuated. Although they are coordinated, but they are actually actuated. Yeah.
You said you feel that many engineers don't know about these options and they aren't widely used. Why do you feel that's the case?
Okay, my case is I've been to different areas, different cities. Like for example, Reno. That's where I started my teaching career. When I got there are a lot of interchanges, diamond interchanges there. And they are just, when they designed it and when they operate it, they all use 2 controllers. And I would consider Reno is not a small city, right? That is about 300,000 people. I would expect they should know that, but they didn't know that. Then, of course, I've been to other areas. I noticed, well, this is the diamond, but it's not really operating as a diamond. So that's kind of my feeling. Okay, go ahead.
I was interested how pedestrian activity plays into this sort of thing. For example, particularly with right-hand turn lane.
Okay, yeah.
You might have more of a delay because there are so many pedestrians, particularly in a very urban area like Portland, that
Okay.
right turn might not be able to make it through before the light changes.
Okay, pedestrian is another interesting issue. Pedestrians still, each phase, whenever there is a crosswalk, you need to provide enough time to let the pedestrian cross. Okay, so how does pedestrian affect the signal timing? It's really the cycle length. See, at night, for example, the volume is so low, we want to reduce the cycle so that we can turn the cars around quicker. But if there's a pedestrian crossing, you need to provide enough time. So that's where it controls your cycle. You cannot run a very short cycle because you have to accommodate the pedestrians. Is that what you...
If there's a lot of pedestrians crossing, sometimes it seems like they cross, they take up the entire cycle and the cars never get to turn right. I'm curious what you do in that sort of situation.
A lot of pedestrians. Okay, in our case, we don't have that many pedestrians. But if you go to Las Vegas, there are a lot of pedestrians. Okay, when we design the timing, usually you provide a walk time that is something between 5 to 7 seconds. Let the people get into the crosswalk. And then the signal will flash. Flash, don't walk. During those times, you can keep walking, so you are safe. By the end of the flashing don't walk, you are safe to cross. But if we got lots of pedestrians, it takes 20 seconds for all the people get into that crosswalk. Then you just have to increase that walk time. So again, if you increase that time, it's going to increase your cycle. So all this impact. Sometimes you also want to protect the pedestrians. You want to separate the conflict between pedestrians and right turns, for example. So in that case, the overlap I mentioned, the right turns, you use overlap to separate the pedestrians. There are different ways of doing that. You can use a leading pedestrian signal, for example. Turn the pedestrian signal on, hold all the vehicles, and then turn the vehicle on. So I could make another presentation if you are interested about the pedestrians. Yeah.
I was just wondering if you slightly increase the delay but reduce the number of stops by not trapping the vehicles in between the 2 intersections, does that have a benefit in terms of emissions?
Definitely. We know the emissions that are related to deceleration and acceleration. Of course, if you stop, you need to decelerate and accelerate. That definitely saves energy, gas.
There's another web question. What would be the effect of having the primary signal use actuators and the following signals tied into the primary release using fixed timing?
The primary, okay, can you say it again?
I don't understand.
I wasn't sure how they mean.
and I mean, that's the thing about the web, is that I can't elaborate.
Okay, it's the same.
What would be the effect of having the primary signal use actuators and the following signals tied into the primary release using fixed timing?
I guess he or she is referring primary as the bottleneck intersection. The intersection has the most problem, the capacity problem, I guess. Okay, so by running actuated, you could increase the capacity. You could increase the capacity of that key intersection versus the other intersections affiliated. They are not that critical, so you may be able to do this. That's my guess. You can call me. What? What's that?
I said, unless he emails again.
Yeah, okay. Well, there are some people watching, huh?
You can wait.
Any more questions?
Oh, yeah, sorry. Actually, I'll throw out one more, since we have one listener who has lots of questions. I understand the queue and spillback problem with the closely spaced intersections, but what if we have more closely spaced intersections on the route and we need the short distance between the intersections for storage purpose? I don't know if that... I'm not exactly sure. Sorry.
Okay, they're closely spaced. How about there's another one closely spaced?
Yeah. I mean, are there instances when you need some of that storage space between the intersections?
Okay. Maybe, I still try to guess. The one I demonstrated for diamond interchange, we try to keep the interior clear. So basically, we are holding the cars outside. So definitely you are going to see a longer queue outside of those two signals. But how about if there's another signal closely spaced to that signal? So that is going to cause queue to the other problem. So instead, you may be able to use the internal link, short link, to store some of the cars. That's exactly what we did for I showed you the PM peak hour. The PM peak hour I mentioned, the cars, they do stop shortly in the middle. And that's exactly what we did. During the other hours, AM, midday, traffic volume is light. There's no queuing problem outside. But the PM peak, we do have that problem. So we release them earlier, a little bit earlier. Let them stop in the middle for a short amount of time. So to reduce the impact of outside of the signals. I think that's what it means.
And then finally, did you get any other public feedback, particularly like after the news story ran, or?
Yes. Then now that everybody knows there's a professor working at UNR that likes traffic signals. So all the complaints that they complain about signals, then the city will forward to me. So I'm starting to respond to the complaints. And actually, there's one professor complained about the signal we did here because one of the phase is kind of short. But if you work, when we did the AM peak, typically AM peak happens between 7 to 8, right? That's when most people go to work. People go to downtown. That's when it happens. That's how we develop the timing. But if you work for the university, what time do you come to the university? It's close to 9, okay? So during those very short period, about 5 minutes, all those cars getting out of the freeway and queued up on that approach. Actually, I personally drove that route every day, and I noticed that. And then after I got this complaint, and I responded, I sent him email. I said, "You must be working at the university." And he said, "Yes, indeed I do. I'm a professor at the math department." Yeah, so actually we just made the adjustment. So I sent an email again. We made the adjustment. Tell me, what do you feel? I haven't heard back from him yet. Yeah.
Just a quick question. When you were going through the 3 intersections that you worked on retiming and the delays and such, you said there was for one intersection there was a recommendation that you made to the city, but they wouldn't let you do it. Have they seen the success of the other things and allowed you to now progress in that direction?
Yeah, they have seen the other intersections. Is first they were reluctant. He was thinking we need to do the rewiring of the cabinet. I told them no, you just need to put a dummy face there. Then I didn't, like I said, I didn't really push that hard. If I'm telling them not change it, probably they are going to change it. But I somehow, as long as we don't get a lot of complaints, I want to keep it there so that I can use that case to show the students.
So stress the public for the benefit of education.
Well, I think with that, before we thank our speaker, just a reminder that next week, Mark Gishard from Metro will be talking about Where the Rubber Leaves the Road, a snapshot of 2 current efforts to manage parking issues in regional centers. So let's thank Professor Tian for his presentation and for visiting us today.
Thank you.